and thanks everyone for joining. As Mike mentioned, what we'd like to do today is get some of you that aren't really familiar with Metal AM, familiar with the design guidelines and rules and on how to select parts for Metal AM. And those of you that are versed in Metal AM, I want to kind of give you more of an idea and a cleaner picture of why Velo3D is different and what the advantages are. So before we dive into the rules, guidelines, etc., I have to take one step backwards and just very high level sort of physics 101, what's going on in laser powder bed fusion. And so one of the biggest issues today is having to need support structures. And the general reason, and this is of course a bit of an oversimplification, is that throughout the laser powder bed fusion process, you're lasing subsequent layers of metal on top of already solidified metal. So you've got something that looks like the graphic in front of you, where you have some metal substrate, you've coated powder onto it, and then you lase it. When you lase it, you melt the powder particles together, and when it solidifies, it shrinks. And that shrink creates stress, residual stress, and it can lead to deformation in the part. And so as you do this layer by layer, you accumulate these residual stresses up that can lead to deformations, distortions if the part isn't constrained very well. What these sometimes manifest in is just a couple different things. And today I'll use the term breakdowns. And what I mean by that is either you've got a geometry that exhibits some surface finish defects. And so you're looking at a conical structure here on the left, and looking at the down-facing surface, kind of looking from bottom up here, you see that the leading edge of growth from layer to layer started to become unstable throughout the printing of this part, and you get these large defects. Large defects can lead to problems with fatigue characteristics, and obviously the elevated surface roughness can lead to problems with dimensional accuracy and with flow characteristics of some parts. Besides just surface defects, the other main breakdown that I'll speak of is warp, right? And so because if you think back to the graphic on the previous slide, you have these top layers melting, shrinking, and trying to pull these leading edges up. You'll have warp, and you can see that this plane at the end of print was supposed to be flat, but it's actually pulled itself up. And this is particularly difficult to control on a down-facing, overhanging surface where there's not much constraint underneath. And so the solution today in general for Metal AM is for all these difficult overhanging geometries to add support structures. And support structures are put in place to basically anchor the part down, to mitigate some of the thermal instabilities that are going on in the leading edge of growth, and to hold that part in place so that it doesn't warp. Warp and the breakdowns are a problem with, of course, the mechanical properties and physical properties of the material. They also become an issue with the recoat mechanisms in most systems. So in general, when you set up a part to print with Metal AM or any 3D printing in general, you start with some sort of solid CAD body like you see on the left, a small cube, and you run it through a print preparation software that basically splits the volume up into specific areas and applies specific processes or laser commands to those processes. And so to use a very simple example here, you've got a solid cube CAD body, and you run it through your print preparation software, and you might have a couple different processes in a simple shape like this. And so what I'm representing here is this green center area is something of a bulk fill area. And those laser commands and that process is optimized typically for throughput and density, but not necessarily optimized for surface finish. So it's very common that you'll split out the bulk fill and the skin, or the very outside surface of the part, into a different process. The skin process is typically optimized for surface finish. The limit of the technology out there today is that the processes are applied in a fairly simplistic way. And what I mean is, on incumbent systems, you may have a bulk fill, a skin process for, say, around vertical orientation, one for if these walls are top facing at more of a shallow angle, and one for a down facing surface. But the issue there is the process that's optimized for say a 60-degree surface from horizontal. I'll use these terms for the angle. I mean 0 being horizontal, 90 degrees being vertical. the process that's optimized for 60 degrees is not necessarily optimized for 40 degrees or 20 degrees. And so when you apply a simple process recipe like this, it doesn't extend into more difficult geometries. And as I mentioned, this is especially true for lower angles or very shallow down facing surfaces. So what Velo3D has done is created a much more comprehensive process parameter set. What I mean is that when you run through our print preparation software, the software automatically applies a very large set of many processes. You may have as many as 24 individual different processes being applied to a single part. They're automatically applied, and each of those different processes create a somewhat continuous blend of process to ensure that if you're printing at a specific angle, that it's optimized for that angle, and so that you don't have surface breakdowns and warp. The goal here is to control the thermal behavior and control the thermal gradients of the part so that you don't lead to these defects. The example I'm showing here is a fairly complicated design. It's a topologically optimized bracket. The one here on the left is set up so that every surface below 45 degrees from horizontal, down facing, is supported. And the object on the left is the same exact geometry, but printed with the design guidelines that I'm going to go through in the next slides. And you can see there's a dramatic reduction in these support structures. So you can get away with printing this geometry, but at the expense of these support structures. They cost time up front for engineering, they cost time to print and material to print, and most significantly probably is that they introduce a lot of post-processing problems. Right? I think anyone familiar with any kind of 3D printing is aware how much time and money and energy can be spent on removing these supports, and then finishing doing things like having to finish the surfaces that were supported, because you're left with a degraded surface finish wherever anything was supported. Okay, so a little overview of the system. So you're thinking about what kind of parts you have, what families of parts you have, and what can be applied to the Velo Sapphire system. So I'll give you a little overview on a basic configuration. So the Velo Sapphire system is a laser powder bed fusion system. So it shares a lot of the same characteristics and fundamental operation and ideas, but with quite a few differences that I'll outline as I go ahead. It's a dual laser system. It has two 1,000 watt lasers. For the bulk fill processes that we use full 1,000 watts so that you can get the full throughput capability of the lasers. Each of the lasers can reach over the full field, the full build area that you're working on. They have overlay capability, meaning if you print a large part over the whole area, a single part, you can use the two lasers together to stitch them. And a clever piece that we put on to the Sapphire system is that we have an in situ correction of these maps. And so sometimes what happens during multi-laser system printing is you'll start out with a well-calibrated system, but because of how the entire system is moving and changing very subtly thermally, structurally, you'll have a little bit of drift of these position maps of the two lasers. It's a very bad thing if you have a single part that's printing with both lasers, because at that seam, you run the risk of having defects. Surface defects to add roughness, or internal defects like porosity that obviously have negative effects on the mechanical properties of the part. Build volume in our system is, it's a round profile, circular profiles of 315 millimeters diameter, 400 millimeters tall. So all of the space is completely usable. And so when you're thinking about trying to fit parts into the system, this gives you an idea of what the maximum size is. Today, fully released materials, Inconel 718, Ti 64. We're in development, in the middle of development with aluminum, F357. And we're moving to others that I'll mention at the end. The powder that we use in this machine is pretty standard. What I mean is it's very typical to other powders that you'd use in other laser powder bed manufacturing platforms. So it's off the shelf with a very standard particle size distribution. The inert gas in the atmosphere is argon. We run at very low oxygen levels. Most of our processes are run at less than 1 ppm. The recoder is quite a bit unique, and without getting into the deep proprietary nature of how it behaves, the result is that instead of having a wiper that smears powder on layer to layer, like most systems do, we have what we call a non-contact recoder. What that means is there's a space between the lowest physical part of the recoder mechanism and the parts. The result of that is that you don't have any interference. And so if you have very delicate geometries being printed, or in some cases I'll get into what we call free floating parts, it's not being pushed and moved by the recoder. And so it opens up a lot of freedom of intricate designs. And most of our processes are run at 50 microns, so kind of pretty standard middle of the road as far as laser powder bed fusion goes.